Today we're looking at trig, and we're looking at the different trig ratios, and all three of the primary trig functions can be traced back to this acronym, Sohcahtoa, capital S-O-H, capital C-A-H, capital T-O-A. Certain letters are capitalized, other letters aren't. First off, the capital S stands for the trig function of sine. We abbreviate it with just three letters, S-I-N. It's not called sin, it's called sine. We're just shortening it a little bit. The sine ratio is opposite divided by hypotenuse. Next, we have CAH. Capital C stands for cosine. It's not cos, it's cosine. The cosine of an angle is adjacent over hypotenuse. And the last abbreviation we have is capital TOA. That stands for the tangent ratio. The tangent of an angle is the opposite divided by adjacent. So we're into a trig unit now, and really what trigonometry is the study of the relationship between sides and angles, particularly in right triangles. We've looked at how to classify sides as opposite or adjacent or hypotenuse, and we're going to use that today to help us get into some of these trig functions. For example, let's go ahead and draw a right triangle. And eventually we can expand this to triangles that aren't right, but we're going to start off with right triangles. And I'll call this angle theta and put in a couple of numbers. How about 5 and 12? Now here's the problem. We want to know what is the tangent of angle theta. This is how the question is phrased. We've done problems like this before, we just haven't phrased them quite in the same way. And what we're told is, from this Sohcahtoa abbreviation, kind of a reminder of what these trig functions are and what those ratios are, is since we want to find the tangent, what is the length of the opposite divided by the length of the adjacent? So from angle theta, I'm looking for the opposite, which is 5. And the adjacent, which is 12, and since it says O over A, my opposite over adjacent ratio, my tangent ratio, is 5 over 12. And that's what it is. Sine, cosine, and tangent, these trig functions are ratios. Sometimes the ratios will be expressed as a decimal. We could divide 5 by 12 and get a decimal. We'll leave it in this exact fraction form for right now. Next one. Let's find the cosine of this angle theta. So we look back up to the top. We have Sohcahtoa. Cosine is AH, adjacent over hypotenuse. I can see that my adjacent side is 12 divided by the hypotenuse. We don't have the hypotenuse yet. However, the nice thing about these trig functions is that they are part of right triangles. And everything we've done with right triangles still applies, specifically Pythagorean Theorem. In other words, 5 squared plus 12 squared is equal to the hypotenuse squared. So we can use Pythagorean Theorem to find that hypotenuse. That's 25 plus 144. Take the square root of that. And we get that the hypotenuse is exactly equal to 13. A lot of times it's going to be some kind of square, some kind of radical that we need to break down. In this case, it's kind of nice that the hypotenuse is an integer. And again, back to the problem, cosine was adjacent over hypotenuse, our adjacent of 12 divided now by our hypotenuse of 13. So there is our cosine. The last question I'm giving you for this one is, what is the sine of theta? Some of these problems you might just be asked to find what is the tangent or just what is the sine. I'm giving you all three of them this time. So based on the triangle that we have, based on the acronym of Sohcahtoa, see if you can write down what is the exact value for the sine of theta. Look at my acronym. Sine is opposite over hypotenuse. It's O over H. The opposite is 5. Hypotenuse is 13. So those are my three answers to this specific problem then. So now we're going to use trig to find the length of a side in a right triangle. And for now, the only way we can use trig is if we have a right triangle. See, there is that little box in the corner, so we know we have a right triangle. We have a length of 14, and the other piece of given information is that we have this angle of 65 degrees. We don't have any other lengths in this one, so we're going to have to use trig in order to find x. From the 65-degree angle, we would call the 14 the hypotenuse. And also from the 65-degree angle, we would call the x the opposite. So I'm classifying the two important sides and how they are related to the 65-degree angle. 14 would be the hypotenuse regardless, because 65-degree angle is where we're starting from. That makes x the opposite. Now I'm trying to figure out what trig function ties all this together. Well, I've got to have the hypotenuse, which means it might be cosine because that has the h in it, or it might be sine because that also has the h in it. It's not tangent that brings these together because tangent deals with opposite and adjacent, and the hypotenuse wouldn't matter at all. Next, x is the one I'm trying to find, and that's the opposite, which means cosine isn't important to me, it's sine. Sine is the one trig function that relates the opposite and hypotenuse together. So here's what we're going to write then. Knowing now that it's the sine function because of the sides we're dealing with, we're going to say sine of the angle. Up till now, we've always been saying sine of theta because the angle was unknown. Now we know that that angle equals 65 degrees, so we're going to write in that actual measurement. So sine of 65 equals the opposite, OH, opposite of x divided by h, the hypotenuse of 14. So there's our equation set up. Quick recap of that. We knew we wanted to use sine because we were given opposite and hypotenuse. And sine is the one trig function that uses opposite and hypotenuse. So we did sine of our angle is O over H, opposite over hypotenuse. Now to go further, to actually find x, we're going to do some algebra. I want to solve for x. If I look on the right side right now, it says x divided by 14. So if we multiply both sides by 14, algebraically, that isolates x, gets it all by itself. And then on the other side, we have to multiply by 14 as well to keep the formula, to keep the equation consistent. Then we'll go to the calculator, multiply 14 times the sine of 65. And we get about 12.69. When we're trying to find the length of a side, always round to the nearest hundredth. Sides always go to 2 decimal places. I can make a quick check of this one to make sure that it seems accurate. In a right triangle, the hypotenuse is always supposed to be the biggest side. So 14 better be bigger than x. If I look at it, it is, so I can be pretty confident then my answer is correct and it does make sense. Good strategy or good habit to get into in dealing with these problems is to write out Sohcahtoa. Eventually you just remember it, but it also can serve as a little bit of a cheat sheet, a guide for you. We're trying to figure out what the value for y is. It's a right triangle. We have an angle. We have a side. We're going to use trig. Pythagorean theorem won't be enough to figure out what y is equal to. I need to figure out which one of these three trig functions is going to be relevant for us. Y is the opposite. It's important because we're trying to find it. 11 is the adjacent. It's important because we know what that is. So as I look at these trig functions, I'm looking for the one that relates opposite and adjacent together. Not the sine, not the cosine. It would be the tangent. Tangent because we're dealing with the opposite and adjacent. So the actual equation then is tangent of 32, tangent of our angle, is equal to OA, opposite of y divided by the adjacent of 11. So there is the geometry or the trig of it. Now algebraically, multiply both sides by 11. That takes care of that denominator. And then take 11 times the tangent of 32. We can actually calculate that, and that gives us 6.874y. Here's another example with using trig to find a side length. From the 40-degree angle, 7 is the opposite. W is the adjacent. Those are the two important ones. I don't care about the hypotenuse. All I care about is the 7 is the opposite. That's nice. And I want W the adjacent. The trig function that relates O and A together is tangents from Sohcahtoa. So the tangent of 40 is equal to the opposite of 7 divided by the adjacent of W. This time our variable is down in the denominator, so it's slightly different than the ones we've seen before. The geometry is no different. Here's where the algebra is different. I don't want W in the denominator. So what I'll do is multiply both sides by W, and that gets it out of the denominator. It doesn't isolate it or get it by itself, but at least it's not in the denominator anymore. So now the equation we have is w times the tangent of 40 is equal to 7. I've got to think algebraically here. Now that w is out of the denominator, what can we do to get w by itself? Claire Sternad would say, how about divide by the tangent of 40? So on the left side of the equation, that all cancels out. You're only left with w. On the right side, you have 7 divided by the tangent of 40. And that's good news for us because we can actually use the calculator to evaluate that for us. Type in 7 divided by the tangent of 40. And since it's a side, we're going to round this answer to the nearest hundredth. W is about 8.34. Quick check on this one. If this is 8.34, 8.34 is bigger than 7. That's true. And the way I know that it's accurate to this problem is that opposite this 8.34 is 50 degrees. There's 180 degrees in a triangle. So 180 minus 90 minus 40 gives us 50 degrees for this one. 50 degrees and 8.34 are bigger than 40 degrees and 7. Bigger side should be opposite the bigger angle. 50 and 8.34 is bigger than the 40 and the 7.